the three flowers.
You better get up on the board, either the side board or front board or wherever you want to go.
So you have your three flowers. As long as they're not in a straight line, this will work.
If they're in a straight line, it won't?
No. You can't get an exact distance from 3 points. So.
Okay.
And then you just kind of make your triangle a little better than that with a straight edge or something. And then you find the perpendicular bisector of all of these, or the perpendicular bisector of all the lines. And so you would cut this in half, so this is the same size as this, and connect it to here. And then you find this point, which these are the same length. And then
now you
cut these.
It's bisecting, but
Bisecting.
is it perpendicular?
It's an angle.
It's the angle bisector?
What did I write on this one?
Either one will work?
Well, okay, yeah, it's supposed to be the perpendicular bisector, so if these wouldn't actually be equal. Never mind.
They wouldn't? What does bisector mean?
Oh, and it would be equal, right? Yeah.
They just always be the same number of, they'd all be different. Like that would be 1, that would be 2.
Or you're saying put different tick marks on. So, yeah, on the closest one, 2, you put a 2 and then 2. There we go. And
Well, yeah,
above,
these aren't the same. These would be the same.
those are the
These
same.
would be the same.
So then
Because
they
I had
should.
this with 1, this with 1, these are 3, and these are 2.
Okay,
Does that make sense?
so that makes it a bisector.
Yeah.
And what else did you say it was?
Perpendicular.
So what does that mean?
So they're
Okay.
supposed to be 90 degrees.
90 degrees.
But I don't know if maybe that's not right.
So go ahead and mark that on your other ones. Does the perpendicular bisector necessarily go through the flower on the on the away from the segment that you're perpendicularly bisecting? You're shaking your head no? Okay. Now why does this work?
Because you find the point of concurrence and that's what's wrong, right? And that's the point that, at that point, it's where they all overlap and it'll all be equal distance.
When we did the two flowers, where did we decide it could be placed? Anywhere on the perpendicular bisector. So if I cut this in half and draw this perpendicular bisector, I can put the sprinkler here and the distance is the same, right? I could put it here and the distance is the same. So by putting in another flower, if I want these two to be watered equally, then what? I have to find the perpendicular bisector of those two. So when I do that, okay, so here's this and here's that, and then we draw this. Anywhere on this perpendicular bisector of this segment, I could put my sprinkler and it will water these two. Well, if I wanted to water all three, then where have I got to go? To the place where these two intersect. Now this distance is the same as that, and this distance is the same as that because we've got two. Does that make sense? Do I need the third one? Do I need the third perpendicular bisector?
No, because it'll meet in the same place.
Yes. Don't you think that's, when two lines intersect in the same place, it's no big deal. But when three do, okay, that's a big deal. So, what does this point we located, which is the intersection of the perpendicular lines, what does it mean? What is the meaning of that point?
Just where you said, when you're comparing 2 points, anywhere on that line could be where you could put the sprinkler. But if you want it to work for all three, you have to say, okay, well, it works here for this one, works here for this one. So that's the only place where you could put it don't know, it just works.
So, I don't see my, yes, here it is. If I were to do this accurately, I just kind of eyeballed it, right? But if I constructed it with my tools, I should be able to put the center of my compass at this intersection point, and it should reach out and be the same distance to all three of those flowers. So I could draw, I could put a circle around my triangle, right? And it would, does that make sense? Okay. All right. Let's talk about these points of concurrency. Shannon used that word here. Name. What we want to do is, there are several triangle centers. We had you build them in your homework. You just may or may not have figured this out. This one here, we did the, we made the perpendicular. Do you guys, do you all know this symbol? Perpendicular bisector. Okay. And what is the meaning of it? What's the meaning of our, we said that that point represents what? Equal distance from all of the vertices of the triangle, right? As such, it is the center of the circumscribed circle. That's getting you some vocabulary. Maybe you circumscribed. We've got a triangle inside here, and we've got a circle that is circumscribed about the triangle. The triangle, we say, is inscribed in the circle. Does that make sense? Okay? And this is the center of the circumscribed circle. Does anybody know the name we give to this point of concurrency, this triangle center? Well, this kind of gives us a little bit of a hint. It's the circumcenter. I'm going to jump to Sketchpad. I'm going to jump to GeoGebra. Does everybody know how to turn this graphics axes off? You just go up here to the triangle and click on the axes and they disappear. Or you want them back, bring them back. If you want a grid there, bring that up. Okay? So, I'm going to build a triangle. Here's my 3 flowers. Okay. And then I'm going to connect them with a segment. And now what? What do we need to do? We need to draw the perpendicular bisector. There we go. And if you mouse over, it'll tell you select 2 points or 1 segment. Or I'll just do that segment and that segment. Now, that point should be the place where the perpendicular bisector here intersects as well, right? Let's just, it's always good, even if you're constructing it with your tools, to double check that by doing that third one to make sure it's in the, okay? Now what I want to do is show you that if I place a point here at, and as soon as I get at least 2 of them to highlight, or 3, I place that there. Now what I'm going to do is I'm going to draw a circle. And so here's my center. Let's see, let's just make sure. Select center point, then point on circle. So if I select this as my center point and put that over on B, notice that it also goes through A and C. And it doesn't matter, the thing about the dynamic nature of GeoGebra is it doesn't matter how I manipulate my triangle, that circle always remains what? Circumscribed about the triangle. Everybody see that? Doesn't matter which one you move, because the circumcenter is always the center of that circumscribed circle. Does that make sense? Okay. Well, in your homework, we constructed the perpendicular bisectors. What else did we ask you to do? Angle bisectors. Okay. When you did the angle bisector, they also intersected at the same point of concurrency, right? All 3 angle bisectors, right? What did you find out about that? What was the meaning to that point? Well, nobody found anything.
Wasn't it the same point? Like if you had done both of them at the same time, they would have met all 6 lines.
Both of what?
Both the perpendicular bisectors and the angle bisectors.
Not necessarily.
That's right,
You
not
can create
necessarily.
triangles where they'll happen.
I can make a triangle where they're not in the same place.
They're not here.
Did anybody do any measurements or any... See, on this one you could have measured from the place where they crossed to each of these points, and what would we have found? They're the same distance. That's why we can put a circle around there, right? But what is unique about this one? Let's just quickly bring up another one. And let's see. Polygon. We could do a... There's our triangle with an actual center in it. Okay, let's do the angle bisector. Which one of these is it on? Right there. And we're supposed to select 3 points or 2 lines. So if I do 3 points, and now I do these 3 points. Now if I draw in the third angle bisector at angle B, it better go through there. What we're finding out, let's try it. And it does. But what is unique about this particular point? Anybody have any ideas? It's obviously not the same distance from D to B as it is from D to C. Right? Yes? It's equidistant from the sides. Let's find out. I'm going to come over here, and when you say equidistance from the sides, how do you determine distance to a side?
Take the shortest path.
Take the shortest path. And the shortest path from a point to a line is always how? Every line is straight. If we were running a race and you and I were both here and you ran there, you want to go how? Down here?
Perpendicular to the line.
Is that what you're meaning to say? Perpendicular. So we want to go this way, right? I could beat you if you ran there and I ran here, even if I'm old and slow, right? Okay, so what I'm going to do is I'm going to create a perpendicular line from a point not on a line. This says select the point and then the line. So I'm going to select this point and this line. Did you see that, how that made it perpendicular? And now I'm going to go get this circle tool. Oops, I better get a point on that. Right there. Now I'll get the circle tool and I'll make the center there and this here so that I'm right on that shortest distance. And now watch what happens as I move my triangle. It doesn't matter the size or the shape. That distance is the same distance to each of the three sides. Does that make sense? Okay. Well, the angle bisector, the meaning is what? Equidistant from what? From all sides, not vertices. And therefore, it forms the center of what?
An inscribed.
Of the inscribed circle. Now we've got the circle inscribed in the triangle, and we said the triangle is circumscribed about the circle. Very different than the last one. Okay, the circle is on the outside with that, and the triangle's on the inside. Okay, and what do you think we should call it? Well, an incenter would be a good name, right? In center, because it is the center of the inscribed circle, whereas the circumcenter is the center of the circumscribed circle. Does that make sense? Okay. And all of a sudden, some of you are thinking, I think I can do that airport problem a little easier now. Or maybe you weren't thinking that. Are there any other things we can make in triangles besides perpendicular bisectors or angle bisectors? Yes, it was in your assignment. What was it? Medians. Let's do, and then we'll do altitudes. Medians. So what's a median?
Point from the vertice to the center of a line, right? The midpoint here.
From a vertex to the midpoint of the opposite side is a median. So if you draw all three of those in, guess what you get? Another point of concurrency. They all intersect in the same point. Let me turn this light back on while we do this one. Right here, I have the model of a thick cardboard triangle. If you'll notice, that distance is the same as that distance. This distance is the same as this one. This one is the same as this, so I have connected the vertex to the midpoint. Vertex to midpoint, vertex to midpoint. This is our new point of concurrency. Okay? what is the meaning of it? Well, we don't really expect you to get this one. Let's see if I can just demonstrate it. If I place the point of my pen just right, this thing will
This is the center of mass.
balance perfectly. You get the idea. It's quite balanced, but okay. Perfect center of gravity of the triangle, or center of mass, as it's sometimes found. In calculus, you'll learn other ways to find the center of mass of a triangle and other objects. For now, we can construct it by just making two of the medians, right? The third one is just kind of a check. Does everybody see what I mean? But when you get two, you already know where that point is. The third median just kind of confirms that you've got the right spot. Center of gravity. You can balance the triangle. Okay? What's the name of this one? It's the centroid. Okay? And there really aren't any circles associated with it. It's this balance idea. Okay, somebody else mentioned, what was the fourth one you had you do? Altitudes. Let's review what an altitude is. Well, just think about it. If this is a mountain right here, is this the altitude? No. What's the altitude? It's the height, right? And height is always the shortest distance from the one to the peak, right? So, just do one of those quickly here. Altitude, we want this one right here, don't we? Select point and perpendicular line, so we do this point and this line, this point and this line. Ooh! It's outside the triangle. This point and the side opposite. But notice all three what? Intersect at the same point. Okay, put my intersection point there. Alright. Now notice if I drag my triangle around, those three lines still intersect. Right? Sometimes it's outside the triangle and sometimes it's inside the triangle. And it looks like sometimes it's even right on the triangle. Okay? This one is called the orthocenter. And I hesitate to give you this last meaning because it's just a bit. Let's just do this. I'll quickly, let's see, I want to do a parallel line. And I want to do it, select the point on the parallel line. So if I select this point and this, okay, I just made a parallel. Now I'm going to select this point and this line. And it made a parallel to this one. Now I'm going to do this point and this line. Okay. Let's see, I need to zoom in just a bit here. This triangle right here. Can everybody see it? Maybe what I ought to do is, yeah, this triangle right here is called an x-medial triangle. X because it's on the outside of the other triangle. Medial because these points A, B, and C are the midpoints of the side of the outside triangle. So x-medial triangle. And you'll notice that this particular triangle, the orthocenter is the what? Center of the x-medial triangle. You see that? What's an x-medial triangle? The triangle outside the triangle we're talking about that we made the orthocenter for. And it's, the sides of it are parallel to the sides of the given triangle that's inside, right? And the points, the vertices of the triangle are the midpoints of that x-medial triangle.
Does the orthocenter apply to us like in a 3D world? Because as I noticed as you moved around, I could see in my mind a 3D picture of it.
All of these will generate to 3D. So if you were to take a tetrahedron, for example, you could create these, all of these, through in 3D.
Well, what I was thinking is, like, if you had 3 plants on the ground, you can have that point D up above it all. And that's what I was thinking in 3D. Well, like, if it doesn't matter, I can see it and just not have it on the ground itself, but like 5 feet up in the air.
So if you had 3 plants and you wanted to water them and then there was 1 plant hanging above, we could actually find the place to put that sprinkler that was putting water out in a spherical thing that would they all be watered the same. Okay. Questions about any of these points of concurrency or triangle centers that we're talking about?
I just have a question just to make sure I understand it right. So with 2 flowers, you can put it in
Anywhere along that perpendicular
right.
bisector.
Yeah. And then, but when you have 3, you can only do 1 because you have to find that center.
Because
There's only
anything
one.
along this one is equidistant from these 2. Anything along this one is equidistant from these 2. But if I want it equidistant from all 3, it has to be where those intersect in order for that to work for 3. Does that make sense?
Yeah, it does.
For the flower problem, if you use the bisector, how would you find
This one or this one?
this one, the second one, not
This
parallel,
one?
just the angle bisector? Because you said that gives equidistance from all the sides, so the flowers aren't on the sides.
That's correct. This would not work for watering the flowers. This one would work for finding the airport being the same distance from each of the roads. Does that make sense? Any more questions? All right. We've got 20 minutes to do this next little thing. Does everybody remember what a protractor is? Let's just review here quickly. If I were going to measure this angle right here with this protractor, I would place, let's measure this angle over here. I would place the point of my protractor right here and one of the edges along the 0, and then I would read the angle here. Is it 130 or is it 50? Because there's both 50 and 130 there. How do I know?
It's 50.
How do you know it's 50?
Because it's less than 90.
Because it's less than 90. It's an acute angle, right? Okay? So be sure you use the right scale when you're reading the... I could have also placed my compass right here with the point there at that same vertex, this ray along the 0, and now I read it, I can still get 50 or 130. Which one am I going to choose? Well, it's obvious it's acute, right? All right. You need to get a blank piece of paper, a full-size sheet of paper. You're going to need to tear it out of your notebook.
On one of the assignments,
Um,
obtuse angle.
Obtuse?
You said it was between 90 and 180.
Correct.
It is. It's never going to be more than 180.
Correct.
So
All right.
what would you call the angle? Because you have an acute angle.
A reflex angle.
Okay.
If it opens more than 180.
Okay.
But then it's not a triangle anymore.
Okay, I'd like this row to draw me the largest acute triangle they can with your ruler on the piece of paper. Largest acute. I'd like this group to do the largest obtuse triangle. Just eyeball it. Make sure it's obtuse. You guys, let's have these four do a right triangle. Okay? And you can use the lines on your paper to kind of get you some, okay? Would these five do me this could be, see if you can get an equilateral triangle. Okay? Can you guys do isosceles? All right. And back here, all of you do a scalene. Okay? If you forget what those words mean, turn to somebody in your group and say, this is what I think I'm doing. Is that right? Quickly, just a big one. And try and fill your entire piece of paper, if you can, with the triangle. Get it as big as you possibly can. As soon as you have your triangle drawn, what I want you to do is take your protractor. I handed you, everybody should have one of these little plastic ones. I handed this out because I wanted to show you a teaching tip. I have a template that I've posted on iLearn. All you have to do is run the template off. It's on a piece of paper. Stick it on the top of your copy machine and put a piece of overhead paper in to copy onto, and you can get, I think it's 12 protractors per sheet. Really cheap. Not only that, they're safer. You get third graders and whacking each other with their protractors. This is hard to do damage, with each other. And I've actually had in junior high, I'll have them punch this with a single hole punch right in the middle and let them put this on their 3-ring binders so they don't lose them. And I'll actually hand out a permanent marker and have them put their initials in it in case they lose it. We can get it back to them. And real cheap. And all right, as soon as you've got your triangle drawn, I'd like you to measure each of the 3 angles, and inside the corner, like this one here, I would write 50. Whatever it measures, inside each of the 3 vertices, write down how big it is. Just measure with your protractor. Some of you have other protractors. You're welcome to use those. Without a calculator, I'd like you to take the 3 numbers that you have written in the corner, in the vertices on the inside of your triangle. The 3 vertices, add them up. No changing them. You have to write down exactly what you get when you add them. And then come over onto this board and write your sum. Okay, as soon as you've got the sum written or figured out, just come up and write it here on the board.
Do you want how you got to the sum or just the sum?
Pardon?
Do you want our angles or just
Nope, just the sum. Just the sum.
Oh, we're supposed to. Yeah. Okay.
those are each one before you consider that.
Let's just see what's happening here. Over here on the board, we see that the sum of the three angles of the triangle are, what would you say? 180. How come we've got a 181 and a 185 and a 177? Does that mean those people measured wrong? How could we get this if you think it's supposed to be 180? Because you're measuring them, you have to make a decision, is this a 32 or a 33, right? And this person may have rounded up each time, right? This one could have rounded down each time, correct? How many of you already knew, before you got into 206, that the sum of the three angles of a triangle add up to 180? I hope so. I hope your education included that. Now, we have a second way of noticing that they add up to 180. What's that? Every one of our arrangements forms what? A straight line along the edge. What is that? What evidence is that? 180 is a straight line, right? In fact, if I'm going skiing and I do a 180, what do? Right here. Straight line, right? Okay. So we've got two pieces of evidence. Our measurements, the thing we tore off. Let's take a look at a third piece of evidence. We'll just use this existing one. I'm going to come over here to my measure menu. I think this is it. I want to, let's see, yeah, measure this angle. And you'll select 3 points or 2 lines. So I'm going to select 3 points. I'll do A first. Whoops. It did the reflex angle. We don't want that, so let's go the other way. Let's go C, A, B. And you'll notice it's what? 49.84. Okay? So, if I want to do this inside one, what should I do? CBA or ABC? Huh? Yeah, this one, and this one, and now it tells us it's 67.49, right? And then B, C, A, and it's 62.68. Does everybody see what I've got? So now down here on the input, I want to take that omega. Let's see, how do I want to put that down here. Do I copy? How can I copy that? Oh, I know what I can do. I can come down here and go to my menu. Where's my menu of symbols? Right here. Okay, so I've got beta, gamma, and so beta plus gamma plus, and then I want omega, and I hit enter. And guess what it gives me? The sum of those, which is 180. And you'll notice, even though I am moving the triangle, and each of those angles is changing, the sum is remaining the same. And you're saying, well, it's broken. So let's just do this then. Let's just do beta and add gamma to that, just the two of them, and hit enter. It's right now 99.17. And if I take and move, notice the individual angles are changing, so are the sums. But that one sum is what? Remaining 180. Does everybody see what I'm talking about? Well, this allows us to look at how many triangles? We looked at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 22 people that I clocked in with that, with their measurements. How many triangles have we been looking at here? As I drag that, I get a new one, right? New. Every little change gives me a new triangle. You can look at quite a few in a hurry, correct? So then, that proves that triangles, when you add the three interior angles together, you get 180. Triangle, you've got the sum on the board, you've got your triangle cut out. Now what I'd like you to do is, I'll demonstrate with yours. Take your triangle and tear a healthy chunk of each vertex off. Just each of the vertices, just tear off a healthy chunk. Like this. So that all you have left is the middle part. Set the middle part aside. Take the three vertices that you tore off and arrange them so that their vertices all touch the same point and they are adjacent to each other. Does everybody know what that word means? Adjacent? Next to is what adjacent means. That's not a math word, that's an English word, right? Adjacent. Okay? And then take a look at how they are arranged together, and then look at how your neighbors is. Make sure that the vertices are all touching the same point.